In this class, we are going to see the operation of the buck boost converter. In the name itself, it is there buck boost converter. The output voltage will be less than the input voltage, also which is greater than the input voltage. So by changing the duty cycle of the switch, we can control the output voltage less than the input voltage as well as the more than the input voltage. Now this is the inductor. This is the positive direction of the inductor current and positive direction of the voltage across the inductor. This is ID, diode current. This is load current. Here we have taken the load voltage reverse. Lower terminal is positive and upper terminal is E2. This is the positive direction of the capacitor current. This is the input voltage. Now to see the circuit operation, we have taken the two cycles of the input voltage. This is the first time period, this is second time period. This is on state, this is off state of a switch. Take the load current as a constant load current. When switch is on, the diode is reverse bias, so the current is passing from source inductor again return to the source. Load requires a constant load current, so the current should be supplied by the capacitor in this manner. If you see the inductor current, which is changing from T1 to T2 during the on state of switch. Once the switch is off, here it is open, the diode is forward bias. Now the current is passing from inductor, load, capacitor. Again, in this manner, the current is passing. In this interval, inductor current will be changing from maximum to the minimum value. Again, on state of a switch, this is the off state of it. If you find the voltage across the inductor, when switch is on, the voltage across the inductor becomes a VL. When switch is off, the voltage across the inductor, which is connected directly across the load, so minus V0. Vs minus VL equal to 0 when switch is on, so VL equal to Vs. When switch is off, VL plus V0 equal to 0. Apply the KVL in this loop. VL equal to minus V0. So from this we can draw the waveform. This is Vs. This is minus V0. This is Vs again minus V0. Now we are going to draw the diode current. The diode is conducting only when the switch is off. When the switch is on, the diode is off. So the diode is not carrying any current. So in this interval, the diode current is 0. Again, during switch is off, the diode current equal to the inductor current. How the inductor current is changing, you take up the same waveform here, maximum to minimum. Again here 0, here maximum to minimum. Now we are going to draw the capacitor current. When switch is on state, the capacitor will be discharges. So the capacitor is carrying a current of minus I0. This is minus I0. When switch is off, apply the KCL at this node. This is entering current, these two are the leaving current. So I0 equal to IC plus ID in this interval. If you find the capacitor current, IC equal to I0 minus ID. We know the waveform for the I0. ID also we know. So I0 minus ID. So at this point, how much current? I0 minus I2, and at this point the current is becomes a I0 minus I1. Again here switch is off. Again the capacitor has to supply the minus I0 current. Nothing but the capacitor will be discharging. In this duration the capacitor will be charging. When the capacitor is discharging, the voltage across the capacitor will be changing from maximum to the minimum value. In this interval, the capacitor is charging, the voltage across the capacitor will be changes from minimum to the maximum. Again decreases, again increases. The voltage across the capacitor which is equal to the load voltage. This waveform which is equal to load voltage, this one. To find the average output voltage, we are applying the inductor volt second balance equation. The voltage across the inductor is 0 over a 1 switching time period. So Vs into T on plus minus V0 into T off whole divided by T equal to 0. Cross multiply this one, we are getting the Vs into T on plus minus V0 into T off equal to 0. We want V0. Find the value of V0. V0 equal to Vs into T on by T off. This T off we can write it as a T minus T on. This T on we can take it as denominator. So you simplify this one. We are getting the equal to delta by 1 minus delta into Vs, where delta equal to T on by T. This is the expression for the average output voltage for the boost converter. Variation of output voltage versus the duty cycle. This is the expression for the average output voltage. Take the duty cycle on the x-axis. We can change the duty cycle from 0 to 1. We have taken the three values 0, 0.5 and 1. Now each value you have taken in this expression, you find out the value of output voltage. If we take delta equal to 0, then we are getting the output voltage becomes a 0. If we take delta equal to 0.5, we are getting the output voltage Vs. If we take delta equal to 1, the above expression, we are getting the output voltage infinity. I have taken the point here. If we line down all these points, which gives the variation of output voltage versus the duty cycle. If the duty cycle less than the 0.5, the output voltage will be less than the input voltage Vs. If the duty cycle is more than the 0.5, the output voltage will be greater than the input voltage. That's why we are calling as a buck boost converter. By controlling the duty cycle less than the 0.5 or greater than the 0.5, the same converter will be operating as a buck boost converter. So thank you very much for watching this video.